My name is Lynch-Aird. I'm going to talk about how gut harp strings are affected by changes in humidity. This work was undertaken jointly with Jim Woodhouse from the University of Cambridge in the UK. I'll start with a bit of background, then I'll describe the experiments we ran and the results we obtained. Many harp players prefer natural gut harp strings over nylon. Jim Woodhouse is giving a talk on why we think this is and how fluorocarbon may provide a better alternative to gut than nylon does. Gut strings, however, are notoriously sensitive to changes in humidity, but the reasons for this sensitivity are poorly understood. The gut strings we used came from Bow brand. These strings are made from strips of washed cow gut. Bundles of gut strips are twisted together, dried slowly under controlled conditions, and then ground and varnished. It would be expected that as the humidity changes, the gut strips would absorb or release water, with corresponding changes in the string linear density. It would also be expected that the gut strips would swell or shrink radially. To unravel the section of string shown here, I simply scraped off the varnish and soaked it in water for a few days. You can see how the soaked section has swollen. It's been claimed that as the gut strips swell or shrink, the twisted structure of the string leads to corresponding changes in the string tension. As the strips swell, the string tightens up. As the strips shrink, the tension falls. If that is the case, then one would expect the effect to vary with the degree of twisting. We define the twist angle as the angular deviation of the twisted string from the untwisted case. The results I'm presenting here form part of a larger study into the effects of varying the twist angle. Bow brand very kindly made up a special set of strings for us. A number of bundles of gut strips were first cut in half, then each half was given a different number of twists. The strings were then dried, ground, and varnished in the normal way. Animal gut is a viscoelastic material. It exhibits both instantaneous or near instantaneous elastic stretching and slower viscous stretching or creep. In the course of testing these gut strings, we began to suspect that a more significant effect of varying the humidity might be that it could trigger additional periods of string creep. This is one of two test rigs we used for these tests. A single string was suspended about 2 centimeters above a solid hardwood base. At one end there's a motorized string winder. When I talk about string length adjustments, I'm referring to the length of string wound on or off the winding pin. At the other end there's a load cell for measuring the string tension, and the string is stretched across 2 bridge pins set at 90 degrees to each other. At the midpoint there's a motorized plucker, which uses a guitar plectrum to pluck the string. There's also a microphone to record the plucks and a temperature and humidity sensor. So the string frequency and tension could be measured directly, and the linear density could be derived using the usual equation for the fundamental frequency of a stretched string. The rig was contained in a wooden box. We used incandescent light bulbs to provide heating. The temperature could be varied by switching on different combinations of light bulbs. There were fans for air circulation, and a metal heat distribution bar to help maintain the same temperature along the length of the string. There was a water reservoir at the back, which usually maintained the relative humidity between 55 and 65%. The shallow tray on the left was used to temporarily boost the humidity level. Adding water to the tray increased the surface area for evaporation. This in turn increased the humidity level until the water in the tray had all evaporated. Since we wanted to investigate whether changing humidity could trigger string creep, it was important to make sure that the strings had settled, that they'd stopped creeping before we ran these tests. To do this, the string was tuned to a target fundamental frequency and then retuned to that frequency every 5 minutes as necessary. At the same time, a 24-hour heating cycle was applied. To monitor whether the string was still creeping, we plotted the string length adjustments required to keep the string tuned to its target frequency against the temperature. When the string was creeping, the graph moved vertically. When it had stopped creeping, or at least near enough stopped for our purposes, the graph showed a repeating cycle, like this one shown in red on the left. We can see from the time response on the right that in this case the string was initially slightly overtuned, and the string had to be unwound from the winding pin as it settled. We already knew from previous tests that increasing the temperature above its previous maximum could trigger additional creep. So to run the main test, the heating regime was changed to hold the string at a constant temperature of 25 degrees Celsius plus or minus 2 degrees. The string tuning adjustments were halted, and the string frequency and tension and the temperature and relative humidity were simply recorded every 5 minutes. This is the first set of results for a string with a twist angle of 24 degrees. The 4 plots are all time responses, with the horizontal axes labelled in days. The top 2 plots show the relative humidity and the string linear density. The lower plots show the string tension and the frequency deviation, measured in cents relative to the starting frequency. The ripples in the responses correspond to temperature variations around the target temperature of 25 degrees. There were 2 larger temperature excursions, which show up most clearly in the tension response, but these did not appear to affect the overall behaviour. The red dashed lines mark the times when water was added to the shallow tray. Each time water was added, the relative humidity initially rose quite quickly, and then remained elevated until the water in the tray had all evaporated. The humidity then fell, again quite quickly, and by the end of the test the humidity was pretty much back to the same level as at the beginning. As expected, the string linear density rose and fell with the humidity. Each time water was added to the tray, the string tension initially rose with the linear density. The first and third dashed black lines mark transition points, where the string tension started to fall even though the linear density was still rising. These appear to mark the beginning of periods of additional string creep, with the string frequency falling quite steadily until the linear density passed its peak. There also appeared to be some sort of threshold effect. On the second occasion that water was added to the tray, the string tension and frequency only started to fall shortly after the linear density had exceeded its previous maximum. In between the periods of apparent creep, the string frequency was hardly affected. There were some fairly significant changes in the linear density and tension, but the effect of these changes on the frequency appeared to pretty much cancel each other out. This suggests that there really is some sort of coupling between the linear density and the tension. This string came from the other half of the same initial bundle of gut strips as the first one. The only difference between them was their twist angle, 29 degrees for this string and 24 degrees for the previous one. The 2 strings were tested at the same time, one in each test rig, and water was added to the shallow trays on the same dates. This string showed very similar behaviour to the first string. Each time water was added to the tray, the string tension initially rose with the linear density and then started to fall, at the same time as the string appeared to start creeping. The string creep rates, however, were more than twice those for the previous string. Maybe this was related to the difference in their twist angles, but we don't really know. This string showed the same apparent threshold effect, with the string tension and frequency only starting to fall on the second occasion that water was added to the tray, shortly after the linear density had exceeded its previous maximum. And in between the periods of apparent creep, the string frequency again remained pretty much constant, in spite of the changes in the tension and linear density. The big difference with this string was that it broke about 2 days after it started creeping for the second time. That's why these plots run for a little over 16 days, whereas the previous plots ran for nearly 29 days. It appeared that literally just changing the humidity was enough to cause this string to break. This is the last one I'm going to show for a string with a higher twist angle of 36 degrees. This string, which was tested at a different time of year from the previous ones, was tested for a longer period and water was added to the tray on 3 different occasions. The first time water was added to the tray, this string showed similar behaviour to the previous 2 strings, with the tension initially rising with the linear density before falling away. It's not really quite so clear when the string started creeping this time, but the creep rate is about the same as that for the first string, despite quite a large difference in their twist angles. This time, however, the apparent creep did not cease when the linear density passed its peak. Instead, the string appeared to continue to creep for about 8 days, albeit at a much slower rate. On the second and third occasions when water was added to the tray, the string linear density never exceeded its previous maximum, and we didn't see any periods of relatively rapid creep this time. The string did, however, show another long period of slow creep after the peak in the linear density following the second time when water was added to the tray. But after water was added for the third time, there was almost no overall effect on the frequency at all. Once again, in between the periods of apparent creep, the string frequency remained pretty much constant, despite the changes in the linear density and tension. So, is what we're seeing really creep? Well, over the course of this test, which ran for nearly 65 days, the string tension fell by nearly 7%, and the string frequency fell by about 3%. The linear density, however, fell by less than 1%. So yes, I think we can be confident that what we're seeing here really is string creep. So what do these results tell us? Well, firstly, we've seen some pretty clear evidence that changing the humidity level can indeed trigger additional periods of string creep. And when the string isn't creeping, there really does appear to be some sort of coupling mechanism between changes in the linear density and corresponding changes in the string tension. We've seen the same behavior across a number of different strings, tested on two different sets of equipment. Furthermore, the degree of coupling between the linear density and the tension is such that there appears to be almost no net effect on the string frequency. And we've seen the same behavior across a range of twist angles from 24 to 36 degrees. This rather suggests that whatever the coupling mechanism is, it's not particularly related to the twisted structure of the string or the twist angle. Maybe it's some sort of volumetric effect, maybe the layer of varnish is playing a role. We just don't know. What these results do seem to indicate, though, is that the useful life of a gut harp string may be determined as much by its propensity to creep as by its inherent yield strength.